Hello there, my name is Harsh and my USN is 069, and today I'm going to discuss on the topic analog to digital converter, or in short ADC. Before moving further on in the topic, let us first see what are analog and digital signals. So by definition, an analog signal is a continuous signal which represents physical measurements, whereas digital signals are discrete time signals generated by digital modulation. So, what exactly is ADC? A ADC is nothing but a tool which is used to convert a continuous time and continuous amplitude analog signal to a discrete time and discrete amplitude digital signal. Some of the real life applications of ADC are ADCs are used everywhere, from our cell phones to microcontrollers. They are also used in digital signal processing and in many scientific instruments. They are also used in music industry, and obviously they are used in computers to convert the analog signal to digital signal. Let us discuss a real life application in detail. So suppose we are talking on a phone. We speak something, the microphone captures the voice and converts this voice, that is the analog signal, into electrical signal, and using the ADC, that is analog to digital converter, this signal is digitalized and is transmitted in the form of radio waves. On the receiver end, the receiver receives these radio waves, and with a separate device called DAC, that is digital to analog converter, this signal is converted back to analog signal for the receiver to hear the information which was sent. So in short, by some way or the other, we are using ADC in our day-to-day life. So now the question arises, why are we using ADC to convert analog signal to digital signal? So let us answer this question. Now, most of the signals which we find around us are analog in nature. These analog signals are susceptible to noise, and apart from this, they are also very difficult to process and store. So we convert analog signals to digital signal using ADC so that the signal can be processed and stored efficiently. Now let us see some of the techniques used for analog to digital conversion. The most common technique used to change an analog signal to a digital signal is called pulse code modulation, or in short PCM. A PCM encoder has the following three processes: sampling, quantization, and encoding. Let us see each of them in detail. Sampling. Before the sampling is done, the input frequency is passed through a low-pass filter or an anti-aliasing filter to remove the frequencies above half the sampling rate to avoid aliasing. We would discuss what aliasing is in detail further in the video. Now, definition for sampling. Sampling is the process of measuring the amplitude of a continuous time signal at discrete instants, converting the continuous signal into a discrete signal. Now, let us view an example for sampling. Okay, so the whole idea is this. When you have a waveform that looks like this, then what we can say that at this point of time, this is the amount of displacement in the vertical axis. And then I'll move forward by a little step of time, and I'll record that down again. So instead of storing the entire wave, we now store amplitude value at particular intervals of time, which would look like this. Quantization. The result of sampling is a series of pulses with amplitude values between maximum and minimum amplitudes of the signal. The set of amplitudes can be infinite with non-integral values between two limits. So we now convert our analog graph to a digital graph. So some of the steps involved for quantization are: we assume that the signal has amplitudes between Vmax and Vmin. Then we divide this the region between the Vmax and Vmin into L zones, each of I d, where d is equal to Vmax minus Vmin by L. The value at the top of each sample in the graph shows the actual amplitude. The normalized pulse amplitude modulation value is calculated using the formula amplitude divided by D. This is also called PAM in short. After calculating the PAM, we calculate the quantized value which the process selects from the middle of each zone. The quantization error is given by the difference between the quantized value and the normalized PAM value. And our quantization process is complete. This is an example for quantization. As we can see, the analog graph was sampled then quantized into this set of discrete values which would be further used for the digitalization process or would be now encoded. Encoding. The digitalization of analog signal is done by the encoder. After each sample is quantized and the number of bits per sample is decided, each sample can be changed into an n-bit code. Encoding also minimizes the bandwidth usage. This ends our pulse code modulation method. Since the pulse code modulation is a very complex technique, other techniques have to be developed to reduce the complexity of pulse code modulation or PCM. The simplest is delta modulation. So the delta modulation works on the concept that it compares the change from the previous value and stores the values accordingly. So we have the following rules for output. If the input analog signal is higher than the last value of the staircase signal, we increase the delta by 1 and the bit in the digital data is 1. If the input analog signal is lower than the last value of the staircase signal, decrease delta by 1 and we increase the bit in the digital data to 0. Modulator. A modulator is a device which is used at the sender's side to create a stream of bits from an analog signal. The process records a small positive change called delta. If the delta is a positive, the process records a 1, else the process records a 0. The modulator builds a second signal that resembles a staircase. The input signal is then compared with this gradually made staircase signal. This is an example of delta modulation technique. As we can see from a graph, initially the analog signal is higher than a digital signal value. So we increase our staircase or we move up a staircase and then we compare the previous state and the current state values. Since the current state value is higher than the previous state, so we store 1 in our data set. Now, again moving forward, we see that our analog signal is still higher than a digital signal, so we still go up the staircase and now we compare our current state and the previous state. Since the current state is higher than the previous state, we store 1 in our digital data set. Now we move further on like this. Now here in a data set, the digital signal is higher than the analog signal here. So now we go down the staircase. While going down the staircase, we decrease our bit by 1. And now comparing both the staircase values, since the previous state is higher and the current state is lower, we store 0 in our digital data set. And similarly, we follow this pattern for the whole analog graph. Aliasing. Aliasing is an effect that causes different signals to become indistinguishable when sampled. Let us understand this with an example. Alright, so we have a sine wave and let's say we want to sample it at this particular interval. So taking samples, we get something that looks like this. Now when we actually use this sample to reconstruct the wave, we notice a problem. The wave we get back looks nothing like the original wave that we've tried to sample. This is a problem called aliasing, and a simple way to describe this would be, if we were to sample any signal at too low a sampling frequency, we are unable to accurately represent that frequency and we end up getting a lower frequency instead. While we've done this video entirely in terms of sound, Aliasing can happen anytime sampling is used. For example, image rendering. See how the checkerboard pattern over here appears to sort of merge together? Well, that's aliasing. So what we are gonna do now is we are gonna move on to the next important topic, that is how do we solve or avoid aliasing. Nyquist theorem. Nyquist sampling theorem is a theorem in the field of signal processing which serves as a fundamental bridge between continuous time signals and discrete time signals, that is, analog signals and digital signals. It establishes a sufficient condition for a sample rate that permits a discrete sequence of samples to capture all the information from a continuous time signal of finite bandwidth. So, according to the Nyquist theorem, the sampling rate must be at least 2 times the highest frequency contained in the signal. It is also known as the minimum sampling rate and is given by Nyquist frequency is equal to half the maximum frequency found in the input wave. And that brings us to the end. I'd like to thank you for your time and attention today. Thank you.